Welcome back, students. In the last chapter, we discussed how we can build wave functions for many electron atoms. In doing so, one of the things we needed to introduce was the Pauli exclusion principle that states that every electron in an atom must have a unique set of quantum numbers. We remember this from Gen Chem. To do this, we had this concept of electrons having a spin up or a spin down. Since electrons are able to have these two spins, we can have two electrons in every orbital, and that gives a unique set of quantum numbers. We also discussed the Aufbau principle, which states that we fill orbitals from the lowest energy up to the highest energy. But in this section, we're going to address the last remaining question of how electrons arrange themselves out into orbitals. And that is, what if we have multiple electrons going into degenerate orbitals? For example, the 2p orbitals. And to do this, we're going to go through chapter 22 and talk about the possible quantum states for many electron atoms. And then we're going to introduce some atomic spectroscopy afterwards. So today we'll begin by talking about electronic terms, levels, and states. All of these are subcomponents of the electron configuration that you know from Gen Chem. So to think about what would happen if we were to put electrons in degenerate orbitals, I want you to quickly pause the video and draw the electron configuration for carbon. All right, so hopefully you paused and were able to draw the electron configuration for carbon. And I am sure that all of you are capable of doing this, and you had two electrons in the 1s orbital, two electrons in the 2s orbital, and then for the 2p orbital, where carbon's remaining two electrons are, you would have an electron or two electrons spin up in two different orbitals, probably the first two. Now, why did you draw it this way? You draw it this way because this is how you learned how to do it in high school and Gen Chem, and your professor or your teacher would say, well, you spread them out like this. This is what they do. And in this section, we are going to look at why they do this. And so in high school and Gen Chem, you called this Hund's rules. And Hund's rule, in addition to the Aufbau principle and the Pauli exclusion principle, were how we filled orbitals. So we'll look at the quantum mechanical versions of Hund's rules, and we'll essentially see that they tell us what we learned in Gen Chem, although they, of course, much more complicated. And so to do this, what we are going to look at is the separation between these various words that we had on the intro slide. So an electron configuration takes into account the quantum numbers n and l. And so this would be, for carbon, this would be a 1s2, 2s2, 2p2 is the electron configuration for carbon. And then the states, so an example of a state is like what you drew, is like how the electrons are arranged. And in between, we have a bunch of different terms. And one of those is terms, which can be kind of confusing. So an electronic term is ways in which we can arrange the electrons that are degenerate. And these are based on the quantum numbers capital L and capital S, and we'll introduce these in the next couple of slides. We also have electronic levels. These are even more in the same energy than terms. They're more important for larger atoms, typically having an atomic weight of greater than 40, or an atomic number greater than 40. And we'll look at those at the end of the lecture here. So what we're going to find out is that there are lots of different ways in which you can arrange these electrons, and there are many different energy levels associated with that. And the lowest energy state is consistent with the way that we would draw these in Gen Chem. And we'll see this as we go on. So the learning goals for this section are going to be to define good quantum numbers, and we'll go over what we mean by good quantum numbers in the next couple slides. And then we'll work with some of these good quantum numbers. And so those are going to be for us mostly capital L, capital S, and M sub L and M sub S. And then at the end, we'll mention capital J and M sub J, which are the good quantum numbers for large atoms. We just saw in the last slide, these various terms are going to be comfortable working with things like configuration terms, levels, and states. And then we're going to see the quantum mechanical versions of Hund's rules and how we apply them. So here we can think about the hydrogen atom, and we can say what operators commute with the total energy operator for the hydrogen atom. And we've done this in the past couple of days, and we know that there were a lot of operators that commuted. So not only did the total energy operator commute, but so did the L squared operator, the LZ operator, and same with the S squared and the SZ operator. And these give us these quantum numbers, 4 of which we don't use quantum number S, but we use N, L, M sub L, and M sub S to describe our hydrogen atom and our electrons in the atom. Now, these quantum numbers are good quantum numbers. They're good because they commute with the total energy operator. And we can know them all simultaneously. So that's what makes them good. It turns out that these numbers are not good quantum numbers for many electron atoms. So if we add in a second electron, we can't describe that anymore. We saw this in the last section. We couldn't solve that analytically. So we had to come up with some other ways around this. And what that means is that we can't actually know all of these quantum numbers at the same time. But it turns out that we can know some other quantum numbers that are, and that makes those other quantum numbers good. And I have in parentheses, I have that they're good enough, and we'll see why they're good enough at the end of the lecture. So the quantum numbers that we will use are capital L and capital S, and we'll also use capital M sub L and capital M sub S. And these capital letters are simply the sums of all of the lowercase letters. And again, we'll see how to apply these as we go on. So you can imagine thinking again in vector terms, which these quantum numbers, of course, are representing. If we have a L, and say we have three different L's, we can sum them up together and get a new vector, capital L. Of course, remember, we can't really know the quantum number L. We could know its magnitude, L squared, and we could know one of its components, LZ. And here you can see a little bit about how we could get this LZ here. Each of these vectors have a Z component. We can add them together and get an M sub L. It turns out that we don't actually need to be able to determine the quantum number capital L. It's much easier to determine M sub L, this capital M sub L here. And if we know that, that's enough for us to figure out what L that would go with. And this follows the exact same rules that our other quantum L and M sub L do. So for example, if we have an M sub L equal to -1, 0, and 1, those are consistent with a capital L of 1, right? We have this M sub L is going from negative L to positive L in steps of 1. All right. So we're not actually going to do any applications of these operators down here, but of course these quantum numbers are due to quantum mechanical operators in the same way that our lowercase L and S and so forth are. And these quantum numbers, so capital L, capital M sub L, capital S, capital M sub S, the operators corresponding to these commute with our total energy operator for small atoms with the atomic number less than 40. So we can know them alongside the total energy operator, and that's what makes them good quantum numbers. So let's actually look at an example here, and we'll look at a helium atom, and we'll excite the helium atom and try to figure out what the helium atom is going to do. To do that, what we're going to need to do is break down the electron configuration of 1s1, 2s1 into different things, and we'll start with terms, and then we can also talk about levels at the end, and a state is, of course, an individual way to arrange this. So let's again think about this excited helium atom. Now, what will this helium atom do? So if we were to draw this naively, we could draw any of these 4 configurations. So we have a 1s electron, we have an electron in the 2s orbital, and either one of those could be spin up or spin down. That gives us 4 combinations here. And now we want to think about what can we say about these various states. So first, let's consider their M sub L and their L. these electrons are coming from s orbitals, and the lowercase l for an s orbital is 0. So all of their uppercase l's, which are simply sums of the lowercase l and m sub l, that's going to be 0. So all of these have an L equal to 0. But what about their S, right? So to get a capital M sub S, which is what we're going to do, we're going to look at their lowercase m sub s's. And the lowercase m sub s quantum number is, of course, plus 1/2 if it's spin up, and minus 1/2 if it's spin down. So we can get a good look on what these quantum numbers are going to be. So for this first case, we have one spin up, one spin down, that's plus 1/2, minus 1/2 is 0. If they're both in the same direction, we have a 1. If they're both in the same direction down, we have a minus 1. And here again, we have opposite, so it's 0. Now, what can we say about the quantum number S? Well, remember that this S and L, these are these angular momentum operators. So if we have an M sub S that is minus 1, 0, and 1, we know that that is consistent with the state that has a capital S of 1, because the M sub S is going to go from minus S to S in integer steps. So these three states here are consistent with having an S state of 1. And then what we have left over is just an MS of 0, and that's consistent with having an S of 0. So these states, and you may have heard this kind of thing before, this state here where we have three states with an S equal to 1 is called a triplet state, whereas this one over here is called a singlet state. And we'll talk more about triplet and singlet states, especially in the next lecture. So what we have is three states that are the same, kind of, they have the same S, and we have one state that is different. Now, of course, what you'll note is that this state on the left side is basically the same as the state on the right side. There's not really any obvious reason why one would be associated with the triplet state and the other one would be associated with the singlet state. And the reasons for that are going to be beyond what we want to go into in the scope of this class, but just know, right, that if we were to have an S of 1, we need to have an M sub S that's equal to 0 as part of that. S is 1, so M sub S is -1, 0, and 1. And we'll see a figure that will hopefully help us a little bit understand this in a couple clicks through here. So the way that we write our terms, so we can talk about these terms, is they're written with a 2s plus 1 up to the left there, and then we have L here. So for this state, our S is equal to 1, and so 2s plus 1 is 3, hence the name triplet state. And then the L is 0, and so for capital L equals 0, we give it a capital S, just like lowercase l equals 0 is an S orbital. And then we have a trend here. So an L equals 0, 1, 2, 3, 4 is gets a symbol of S, P, D, F, and then after F, it just goes on down the alphabet. So it goes G, H, I, and I think we'll probably cut off at I. There's some tables in the book and so forth that have I orbitals, and I'm sure it goes on longer than that if you want to do that. So these terms, like I said, we get the singlet term, well, 1s term and a 3s term for a triplet term. The terms are 2s plus 1 times 2l plus 1 fold degenerate, and we'll see some more of this in the future. So since L is equal to 0 for both of these, we see there are 1-fold and 3-fold degenerate. And they have some wave functions. Again, don't worry too much about these wave functions, but you could work with them and understand, where they come from. And it turns out, and this is pretty important for things like spectroscopy, we'll see this in the future, that the triplet state is lowest in energy. And this is corresponding to Hund's rules, and we'll see Hund's rules later. So let's look at that picture. I said we'd look at it a little bit later. And here we have it. We have, and on the left-hand side of this picture is the singlet state. And in the singlet state, we have electron spin. So here we have a spin up and we have a spin down, and they are exactly opposite of each other. And that gives a total S equal to 0. However, in this case, we still have a spin up and a spin down, but they have x and y components that add together, although their z components cancel out. And so when you add these two vectors together, so this, for example, would be this state here, we still see an s, a total s, which is the total magnitude of their spin angular momentum, that is still equal to 1. And then, of course, and these other two examples, if they're both pointing up or both pointing down, it's pretty easy to see how we could have an s equal to 1 or for ms equals 1 or ms minus 1. So here it seems pretty complicated. We have 2 electrons only in helium, and we have a whole bunch of possible states for this excited state. So how could we talk about more electrons in an atom, so something like lithium, carbon, oxygen, so forth? It turns out that there's some simplifications that we can draw for these many electron atoms. So we're going to think about which electrons affect the energy or the configuration that we can draw. And so the way that our energy is going to be impacted, and we'll see this when we see Hund's rules at the end, is that energy depends on the quantum numbers capital L and capital S. And these are, of course, dependent on the quantum numbers m sub L and m sub S. So I want you guys, again, to pretty quickly here pause the video and determine the electron, or the m sub L and m sub S for all of the atoms from helium to neon. And what I mean for you to do is determine these m sub L and m sub S for the ground state of these atoms. So simply, draw out your electron configuration like you would from Gen Chem, and then add up the components of m sub S and m sub L and see what you end up with. So what we see when we do this is that our complete subshells have an S and L equal to 0. So helium, since it has 2 electrons in the same orbital, one is spin up and one is spin down, so those cancel out. And then L is only equal to 0 because it's in an s orbital. Now, once we get into p orbital atoms, well, let's look at beryllium first. So beryllium, that also has an s2 configuration, has an m sub L of 0 and an m sub S of 0. Once we get into the p's, right, we can see that for neon, so for P1, 2, 3, 4, 5, those are all different. But neon, again, has a full s and a full p orbital. And so its electrons, they're all, every spin up electron's got a spin down electron. Every L equals 1 electron is an L equals minus 1 electron. And so these cancel out. And so all of these terms, all of these electrons that have full orbitals will have the same term. They all have m sub L equals 0, m sub S equals 0, and that gives them a 1s term. Now, what can we say if we have many electrons in different orbitals and we have different L's and so forth? What we can do is as follows. So if we have electrons in different orbitals, how many ways can we arrange these things? Well, first of all, we recognize that these electrons are independent, which actually makes the problem easier for us. So the possible number of states we can have is this horrible expression I've written here that's actually pretty straightforward. So it's 2 times 2L plus 1. And so what this means is that if our L is 1, right, we have a p orbital, and there are 2 plus 1, 3 p orbitals, times 2, 6 possible arrangements because they can have either spin. So electrons in p orbitals have 6 ways to arrange themselves, electrons in d orbitals 5, s orbitals 2, and so forth. So if we had an electron in a p orbital and an electron in the d orbital, we would have 6 times 10 for 60 possible different combinations that we could arrange them in. Now, the way that we can determine what terms are allowed is as follows. We use what's called a Clebsch-Gordon series. And simply, we say that our capital L is equal to the sum of our lowercase l's, and then it descends down to the difference between them. So, okay, how do we use this? Well, again, going to the example of a p and a d orbital, well, let's start with s and p. So if we have an s orbital and a p orbital, right, L for the s orbital is equal to 0, L for the p orbital is equal to 1. So the highest L it could have is 1, and the lowest L it could have is 1, right? Because 1 plus 0 is the same as 1 minus 0. Now for a p and d orbital, now it will be different. So now we have 2 and 1. So now their highest would be 3, L plus 2 plus 1. Their lowest would be 2 minus 1, which would be 1. In class, we'll go through examples if you're interested about s, p, and d orbitals if you have the same thing. The book goes through this as well. Essentially, what you do is just calculate one. So we could calculate what we would do for an s and a p orbital, and then put that together add a d orbital into there and do another series and come up with this as well. And we do the same thing for s. So here in these two, s is 1 or 0 because we have 2 electrons, so they can either be both spin up or opposite, and so we have this s and 1 and 0. Here we have 3, so we have 3 halves and then 1 half as we descend in steps of 1. And then we can get the terms are just the combination of all of the possibilities. So if for the s and p combination, we have an L equal to 1 and an s is either 1 or 0, that means our possibilities are 1p or 3p. And remember, these terms are 2L plus 1 times 2s plus 1 degenerate. So this 1p term is 3-fold degenerate, and this 3p term is 9-fold degenerate. And there should be a total possibility of 6 times 2, 12 states, and we can see that here in these terms. And we can do the same thing here for these other orbitals. And again, we'll go through some physical examples of these in class. Now, it gets harder if the electrons are in the same orbital. And we'll look at this here. So this is harder because if the electrons are in the same orbital, say for ground state carbon, instead of an excited state carbon like we looked at last time, the electrons are dependent on each other. So we can't have any single configuration of a p orbital and any single configuration of another p orbital electron in those orbitals because they can't be in the same spot. And so how many ways can we arrange them? Well, we can arrange them this many ways, and this looks pretty complicated. Maybe I made it unnecessarily complicated, but it's pretty simple. So in the numerator here, we have 2 times 2L plus 1. We saw that on the last slide. If L is equal to 1 for a p orbital, then 2 times 2L plus 1 is equal to 6, because there are 6 options for where the electron can go in the p orbital. In the denominator here, I is the number of electrons. And so what we have, say if we had a p orbital and 2 electrons, this would be 6. This would be 2, and this term here would be 4. So in the numerator, we have how many ways can we arrange the electrons. In the denominator, we have how many electrons are there, and then how many empty spots do we have left for those number of electrons. And this is how we can calculate how many number of states that we have. So in the textbook and on the homework assignment for today, you will look at doing these for carbon. And I'll go through an example right now of doing this for oxygen. And remember, these actually end up having the same answers. We just saw that a couple slides ago. So how do we go about doing this? I'll bring us to the board and then we will discuss. All right. So here we have oxygen, and it is a P4 atom. That's its electron configuration. And we can see by using that equation that we had before, there are 6 possible places for electrons. There are 4 electrons and 2 empty spaces. And if we go ahead and solve this equation by just evaluating what these factorials are, we get a total of 15 possible states that have this arrangement. So what that means is that there are 15 ways in which we can arrange these electrons for oxygen. And what I would like you to do, again, is just pause the video, go through and try to arrange these. I will arrange them as well here, and then I'll pause the video and resume, and we'll get back to all having all the same state. So for example, I'll do the first couple and then you can follow along. So the way that we're going to do this is just by drawing out these 3 lines and then putting in the electrons. So one possible way we can put in these electrons is like this. Now this probably looks wrong to you, and this is right. This is not the lowest energy term, and we'll figure out why that is. But another way that we could arrange this is simply we could have up, down, down, down. And so there are going to be 15 ways in which we can arrange this electron configuration. I want you to go through, see if you can find the remaining 13, and then meet back with me when you're done, and we'll compare and then see what terms we can put these into. Now we have all 15 of our possible states for oxygen. And so what we need to do is determine what are the M sub L and M sub S for these states. So here I've arbitrarily decided that the first one is M sub L equal to 1, and then 0, and then -1. So for this first state here, if we were to sum up their M sub L quantum numbers, we would get 1 + 1 + 0 + 0, which is 2. And if we sum up the spins, we get up, down, which is 0. We can go through and assign the rest of these energy levels here. So I'll do that. You can do it along with me. You can pause and do it yourself and then check your work. But we simply have, I'll do them one at a time. So for the second one, we have 1 and -1. Then we have 1, 0, 1, 0, 1, 1, 0, -1. 0, 0, 0, 0, 0, 0, 0, 1, -1, -1, -1, 1, -1, 0, -1, 0, -2, 0. All right, so at this point, we have our M sub L's, we have our M sub S's. Now, how do we actually group these into terms? Remember, terms don't depend on M sub L and M sub S. Terms depend on L and S, and we write them as 2S + 1 L. So the way that we go about figuring out what terms are possible is, again, simply looking at the M sub L. So we'll start here, and we'll say that this first state has an M sub L equal to 2. And we'll notice that it's the only one with an M sub L equal to 2. And it also has an M sub S going along it that's 0. So these two combinations of having an M sub L is equal to 2 with an M sub S is equal to 0 is consistent with an L equals 2 and an S equals 0 term. And that, again, plugging these numbers in up here, that would simply be a 1D term. So what we need to do is find states that are consistent with this 1D term. This should have L equals 2, S equals 0. And so that means that all of the M sub S's should be 0, while the M sub L's should go from -2 to -1. So we can find states that are in corresponding with this that have, so we have a 2, 0, a 1, 0, a 0, 0, a -1, 0, and a -2, 0. And these 5 states correspond to a 1D term. Now let's look at the next one. Below that, here we have an M sub L is equal to 1 and an M sub S is equal to -1. And we could also, if we wanted, we could go down at this one as well. So let's box out this here. We have a 1 and a 1. And the same is going to be true depending on what we look at. So this is consistent with an L equal to 1 and an S equal to 1 state, which would be a 3p state. So what we need to do then is find states that have L equal to 1, 0, and -1, and M sub L equal 1, 0, -1, and M sub S equal to 1, 0, -1. So here we have a 1, 1. Let's find a 1, 0, and then we have a 1, -1. And then we look for a 0, 1. So here we have our 0, 1, our 0, 0, our 0, -1. And then we should have a -1, 1, a -1, 0, and a -1, -1. What we're left over with then is simply one state with an M sub L and M sub S is equal to 0. So this is an L equals 0, S equals 0 state, which is a 1S term. So we have 3 possible terms here for the ground state oxygen atom. We have a 1D term, a 3p term, and a 1s term. Now, what we want to do is try to figure out which one of these states is the lowest in energy. Now, our gut is telling us that this state is lowest in energy. And what's going on with this state? Well, let's track it down here. So this state is shown right here, and this is in this 3p term. So is the 3p term lowest in energy? It turns out that it is, and that's basically what Hund's rules are. So Hund's rules are going to tell us that the 3p term is lowest in energy, which means this way of drawing the electron configuration is the best way to draw the electron configuration because it is a state that is consistent with the lowest energy term. Now, what we don't get when we draw it in this way is that there are also 8 other states that are consistent with the lowest energy term. And this kind of makes sense, right? For example, we can look at this one down here. This one's also good. And it's basically doing the same thing as the way we would draw it. It has one set of paired electrons, and the other 2 electrons are pointing in the same direction. But that's not true for every state that corresponds to this term. And again, the actual relationship between these is a little bit more complex than we certainly went into in Gen Chem. And here we can finally get a chance to lay hold of it and discuss it. So let's go back to the slides here, and we can see again, this is a breakdown for doing it with carbon. So you'll look over this as you do your homework. What we can see is the list of all the possible term symbols for all of the possible ground state configurations. So we developed this here for oxygen and carbon, but we could also do this in theory for any possible state. It gets, of course, much more cumbersome the more electrons and more possibilities that we're dealing with. So this brings us to actually stating Hund's rules. And so what Hund's rules are trying to get at are how can we arrange these? How can we figure out what the lowest energy state is? Our gut is telling us it should be something that goes along with that 3p state, but what is it? So what Hund's rules are as follows. There are actually 3 rules. We'll look at the last one on the next slide. The first rule is the lowest energy term has the greatest spin multiplicity. So that is S. So it has the largest S. So if we go back and look at our possible states here for carbon and oxygen, we would figure out that these 2 terms have an S equal to 0. This has an S equal to 1. So the greatest one is S equal to 1. That means this 3p term is the lowest energy term. So Hund's rules have told us that 3p, the way that we want to draw it, is in fact the lowest energy term. The second of Hund's rules is that if there is the same spin multiplicity, so if we have 2, for example, 2 singlet states that we just saw for carbon, the lower energy term is the one with the greatest orbital angular momentum, which is the largest L, is the lowest energy term. So for us, for our carbon atom, the 3p term is lowest in energy, followed by a 1d term, followed by a 1s term. And I have another example down here. That the first thing we care about is S, and then after S, we compare L. And that gives us our differences in our energy terms. So this is consistent with our idea of how we thought it should be from Gen Chem. The fact that our intuition from electron configuration coming from Gen Chem is consistent with the lowest energy term allows us to actually have a shortcut that we can use to determine the lowest energy term. And I'll go through this pretty quickly here as how we can do this on the whiteboard. Rather than finding out all of the possible terms, this shortcut allows us to figure out the term that corresponds to the lowest, or state that corresponds to the lowest energy term. So how could we determine easily the lowest energy configuration or term for any atom? So what I have here is the electron configuration shown if we have a p1 atom, for example, like boron. And remember, the rest of the states don't matter. So when you have, say, a full s orbital, the +1 and the -1 of the electron spins cancel out. And we'll see here that if it will fill up the p orbital, so that doesn't matter either. So what's the lowest term for this? Well, all I have to do is figure out what capital M sub L and capital M sub S is. In this case, we have a single electron. So this electron spin, M sub S, is the sum of 1/2. There's only one, so it's spin up. Now, what's M sub L? Well, M sub L here is the sum of all the lowercase m sub L's. And I figured out arbitrarily what the maximum one is. So I start with 1, and then I go work my way down. So here, M sub L is equal to 1. So what is the term that's associated with this? Well, we simply assume that our M sub L is our L, and our M sub S is our S. and then plugging it into the form of 2s plus 1l, we can get that the lowest energy term for P1 atoms for boron is 2 times 1/2 plus 1, which is 2, and then L equals 1, which is P. So it's a 2P configuration. What about P2? Well, we simply put in another electron. Now my maximum M sub s is no longer 1/2, it's now 1. And so I would just put that in, and this would give me a 3P configuration for my lowest energy term. What about P3 configuration? Again, it's pretty easy. Now my M sub s and M sub l have changed. My M sub l is now 1 plus minus 1, which is 0, and my M sub s is now 3/2. So this gives me a 4s as my lowest possible energy level. And then I would go through, if I repeat this, we'll find a reversal here. So if I put in my P4 configuration, it's the same as P2, and my P5 configuration is the same as P1 as I do this. Now, when I'm full, I see that my M sub L and my M sub S are now both equal to 0. So my lowest energy state for, say, a P6 configuration is a 1s state. And this is true for P6, it's true for S2, it's true for D10. Anything that's full has this 1s configuration. Let's go a little bit more complicated. Let's do a d orbital, and we can give it, let's just give it 4 electrons to be spunky here. Now, what's the lowest energy configuration for this term for this D4 configuration? Well, all we have to do is list out our M sub L's. So we'll say this is 2, 1, 0, minus 1, 0. Our M sub S here is 2 or 4 times 1/2, which is 2. And our M sub L is 2 plus 1 minus 1, which is equal to 2. So our lowest energy term there is 2 times 2 plus 1, which is 5. And then we have an M or an L equal to 2, which is a capital D. So a 5D term is the lowest energy term for this state. The last of Hund's rules is relevant when we look at more with larger atoms. So when you have larger atoms, it turns out that these terms can actually be broken down further into energy levels. This is going to be true for all atoms, but it's only relevant for larger atoms. And this is because once we get to larger and larger atoms here, more protons in the nucleus, these L and S quantum numbers are no longer good enough, and there's differences between them that become apparent. So what we can do is split them up even further into energy levels. And the reason behind this, as you can see in the title here, is that there's a coupling between the electron spin angular momentum and the orbital angular momentum, and that kind of interferes with this. So we get a quantum number J. Here we have operators J squared and J sub Z. These commute with H, and they are the new good quantum numbers. Our J is equal to L plus S, and then L plus S minus 1, all the way down to L minus S, another Clebsch-Gordon series. And then M sub J is plus or minus J minus 1, and so forth down to 0. So what we can do is split up these terms into levels. So for example, our 3P term here has an L equal to 1 and an S equal to 1. So that means it has a J that could be 2, 0, or 1. So it goes from 2 to 0, and it takes integer steps in between there. And then it would have an M sub J, or plus or minus J. So the J equals 2 would have 5 terms, the J equals 1 would have 3, and then the J equals 0 would have 1. And we can split these terms up. So in this case, the way we would write this, we write these symbols as 2s plus 1 L J. So our 3P term here becomes a 3P2, 3P1, and 3P0 term. And our 1s and 1d terms, since s is equal to 0, there's only one level associated with each of them, but that would become what L is. So we have a 1s 0 level and a 1d 2 level, but there's only one level because our quantum number, capital S, is equal to 0 for both of those. Now, this is true for every single atom here, is that we could split these terms up into levels. Now, we don't necessarily need to do that because it's often beyond our resolving power to identify. And you can see this here. So this is shown for carbon. you can see that the difference between the lowest energy state and then the middle state and the highest state, each state is about 10,000 inverse centimeters apart. So it's actually 10,000 and 11,000 inverse centimeters apart, which is a lot of energy. So there's a lot of energy between these electronic terms, which is why in electronic spectroscopy for non-hydrogen atoms, we see a whole bunch of spectral lines because we have a whole bunch of energy level transitions that are possible. These are about 40 inverse centimeters apart. So the difference between P0 and P2, or 3P0 and 3P2 is 40 inverse centimeters, and the difference between 3P and 1S is 20,000 inverse centimeters. So since 40 is so small, we really can't resolve that ever, so we tend to ignore it. For larger atoms, that becomes larger, and it becomes more of a difference, and so we can't ignore it for larger atoms. Hund's third rule is that if the unfilled subshell is exactly or more than half full, the level with the highest J is lowest in energy. If it is less than half full, the level with the lowest J is highest in energy. So carbon with 2 electrons is not half full. So that means we go for this bottom part of the Hund's third rule. So the unfilled subshell would have the lowest J is lowest in energy. So that would be 3P0 as shown here. For oxygen, like we did the example of, the 3P2 energy level would actually be lower in energy because oxygen is more than half full. All right, so we'll leave this here. This is basically all I want you to be able to do with these quantum numbers. And again, we can spend the whole time in class going through examples of this. It's not that hard once you get the hang of it, although it seems very intimidating. And the greatest thing is that it agrees very well with our intuition as to what these energy levels should actually be. And next time we'll look at some applications of this and go through some spectroscopy.